Okay, another set of applications that involve derivatives are related rates. With related rates, we look at variables that are related in some way. If we know the rate of change for one variable, we can find the rate of change for another. As we solve related rates problems, these are the steps that we want to move through. First, draw a picture if that's helpful for you, and name the variables and constants. And you want to make sure that you use t for time and assume that all variables are differentiable functions of time. Write down all the information that you have using the symbols that you have, or that you've chosen. Write down what you're asked to find, which is usually a rate, and rates are expressed as derivatives. Write an equation that relates the variables. You may have to combine more than one equation together to get a single equation that relates the variables whose rate you want to the variables whose rates you know. Occasionally you'll have an equation for which you may not know all of the rates, and you may have to combine it with another equation to get a single equation for which you know all the rates except for the one you're looking for. Next, differentiate with respect to time, and you want to express the rate in terms of the rate and the variables whose values you know. And evaluate. That means use known values to find the unknown rate. Now, the most important thing to remember off this is that you evaluate at the end. So possibly you're doing a problem where you know the radius. Don't plug that value in until it's the end. You get to the end of the problem unless it's a constant. But if it is a variable, do not plug that value in until the end. Now here it says, how rapidly will the fluid level inside a vertical cylindrical tank drop if we pump the fluid out at a rate of 3,000 liters per minute? Now, you can think of a vertical cylindrical tank as like a soup can. And we know when we find the volume of a tank, a cylindrical tank like this, we are looking at the area of the base, which is a circle, which is pi r squared, times our height, which is h. Now notice that this problem we are dealing with liters, so we will need the formula that uses volume in terms of liters. So our formula here is going to be volume equals 1,000 pi r squared h. Now remember that the 1,000 comes from the fact that we have 1,000 cubic meters in a liter. Or I'm sorry, one cubic meter is equal to 1,000 liters. Okay. Now let's look at what information we know. Well, if we have a cylindrical tank and we're pumping fluid out of that tank, then our height is changing. And that's what we're looking for. How rapidly will the fluid level drop? So we're looking at how the height changes. Now, if I have a cylindrical tank, then the radius is going to be a constant. It's not going to be changing. It's going to be set all the time. The radius never changes as we are dropping the height in this tank. But the volume is changing. We're given that information. We're told the change in the volume. The volume is changing with respect to time at a rate of negative 3,000 liters per minute. Now I know that that is our rate of change because it is being pumped out at 3,000 liters per minute. Now what the question asks us for is to find the derivative of our height with respect to time. We want to know how quickly the fluid level, the height, is dropping. Okay, once we know, look at what we're given, what we want to find, and come up with an equation, then we're going to differentiate. We're going to take the derivatives of both sides with respect to time. So here, the derivative of the left-hand side will be dv dt. The derivative of the volume with respect to time. Now the right-hand side may at first look like a product rule, but remember r squared is a constant and we need to treat that as a constant. So this is like having a constant coefficient times h. And remember, h has an exponent of 1. If you subtract 1 you get h to the 0. So the derivative is just going to be 1,000 pi r squared. Now we are differentiating with respect to time, so I'll need dH dt. So each time that we differentiate one of our variables, we'll have to include this dv dt or dH dt. Okay. Now once we differentiate, we want to plug in the values that we know. And the only thing we were given was the change in volume. And the change in volume is negative 3,000. So negative 3,000 equals 1,000 pi r squared dH dt. Now what we're asked to find is dH dt. So I'm going to divide both sides by 1,000 pi r squared. And I'm going to simplify. 1,000 goes into the bottom and into the top, so that's going to be negative 3 divided by pi r squared. And that is the change in our height, or the fluid level, with respect to time. Now notice that I need to know what the radius is. So depending on what the radius is, that tells us how quickly the fluid level will be dropping. If I have a smaller radius, then it's not going to take near as much time to pump all of the fluid out of this tank. The larger the radius, the more time it will take to pump the fluid out. Now if we are given a radius, let's say that r is 10. So if we have a radius of 10 meters, then the change in our height with respect to time when r is 10 would be negative 3 divided by pi times 10 squared, or negative 3 divided by 100 pi. Now if you type that into your calculator, you'll see that that is approximately negative 0.0095. And it's in meters, and we're talking about, our change was liters per minute, so this is going to be meters per minute. Okay, so the change in the height, if we had a radius of 10, is negative 0.0095 meters per minute. Now let's look at another example. We have a hot air balloon that's rising straight up from a level field. It's tracked by a rangefinder 500 feet from the liftoff point. At the moment, the rangefinder's elevation angle is pi over 4. The angle is increasing at the rate of 0.14 radians per minute. How fast is the balloon rising at that moment? So what we know is we know the rate at which the angle is changing. The change in the angle with respect to time is 0.14 radians per minute. We want to find the change in our y, if you look at the picture, which is the change in the height. So we're looking for how fast is that balloon rising, so the change in the height. Now notice that along the bottom of the picture there you have 500 feet. That is a fixed value. It's not going to change. So we have information about the angle. We know this side of our triangle, and we want to find information about this side of our triangle. So we have to look at what relates this angle to those two sides. And if we look at that, we have an angle, it's opposite, and it's adjacent. So we will use tangent. So we have the tangent of theta is y divided by 500. Now that relates the information that we're known. And we know the change in theta, and we want to find the change in y. Okay, so let's summarize what we know. We know our change in theta with respect to time is 0.14 radians per minute. And we know we want to find dy dt when our angle is pi over 4. And the formula that relates those is that the tangent of theta is y over 500. Now the first thing I'm going to do is I'm going to multiply both sides of this equation by 500, and that will give us 500 tangent theta equals y. The reason I'm doing that is we're going to be looking for the change in y, so I'm going to get that y by itself to begin with. Now I can go through and differentiate. On the left I have 500 tangent theta, and 500 is a constant multiple. When we take the derivative of tangent theta, that's secant squared theta. But remember, once we take the derivative, we've got to multiply by the change in theta with respect to time. Now on the right-hand side, the only information we have is y, and so we're going to be taking the derivative of y with respect to time. And that's what we're looking for. We're looking for the derivative of y with respect to time. Now we're looking for that derivative at a specific place. We're looking for that derivative where theta is equal to pi over 4. So we're going to be looking at dy dt when theta is pi over 4. So that will give us 500 secant squared pi over 4 times d theta dt, which was information we were given, 0.14. Now remember that the secant of pi over 4 is the square root of 2, so we're going to have the square root of 2 squared. Well, that will be 500 times 2 times 0.14 will give us 140. And here our problem was in feet. And notice that the angle was changing by the minute, so this is feet per minute. So the change in our elevation with respect to time when the angle is pi over 4 would be 140 feet per minute.